Everybody, I'm going to talk about aromaticity today as kind of an introduction to what we're going to dive into next, which is the reactions of benzene. But before we do that, we need to kind of understand a little bit more about what benzene is actually and what an aromatic compound actually is. So I have just a selection of cyclic conjugated systems here. So, we've got the pi bonds alternating. They are cyclic. I've got a p orbital on every atom in the ring. So you can see that there's a lot of similarities here, but if we actually look at them, so we know that benzene is incredibly stable. Okay, so we know we've seen that one before. The other two are a little bit more unfamiliar, but we know that benzene has that incredible stability, which makes it pretty much unreactive to most things, pretty much everything that we've seen so far. So this guy, cyclobutadiene, it is actually incredibly unstable. Okay, so we'll see a little bit of why that is. And then the cyclooctatetraene, that one actually is pretty much like a normal stability type molecule. To the point that the alkenes that are in it are just going to behave like normal alkenes in any reaction that you would run on an alkene. They could do addition reactions, they can do all of that stuff. So what's really the difference between these three that gives us that very different energy levels? Okay, so benzene is aromatic. Okay, so that aromaticity gives it incredibly low energy. Okay, versus if we go to the cyclooctatetraene on the right, because it's kind of normal stability, this is actually a non-aromatic compound. Okay, so we'll call those like non-aromatic. It doesn't fit into the aromatic category, and it doesn't fit into anti-aromatic, which is our cyclobutadiene. Okay, so anti-aromatic is incredibly high energy. And because they are so high energy, they're actually quite rare. There aren't that many examples of true anti-aromatic compounds, as we'll see why in a little bit. So the non-aromatic is probably the majority of chemicals or compounds. There's a ton of stuff out there that's non-aromatic. There are a lot of aromatic compounds as well, but these things are very common. Okay, a lot of the stuff that we work with falls into the non-aromatic category and is just kind of normal energy levels. Okay, so to really understand why we have these categories or how we have these categories, we need to, so I should have done it there. We need to kind of think about what is actually the criteria for aromatic versus anti-aromatic. Okay, so what kind of criteria are we looking for here? So the first thing that they have to be cyclic. Okay, so if they don't hit any one of these criteria, they immediately are going to fall into the non-aromatic category. So this is pretty much just if they hit all of these things, we're aromatic or anti-aromatic. If they miss even one, then it's automatically going to be non-aromatic. So you can imagine all of the compounds that we have that are not cyclic are immediately going to be non-aromatic compounds. okay? The second thing that they have to do is they have to be planar, okay? And when you have small ring sizes and you have them conjugated, it's very, very difficult to not be planar. But we'll see why exactly we, how we can think about things being planar. Or you can try building it with your model kit. There are definitely ways that you can figure out planarity. Okay, so the third criteria is they have to have a p orbital on every atom in the ring. Okay, and note that I didn't say anything about that it has to be pi electrons or anything like that. It just has to have a p orbital. So that means stuff like carbocations can count, right? Because they have a p orbital present. And then the fourth is it actually matters the number of electrons that you have in that conjugated system, okay? That's called Huckel's rule. Okay, so Huckel's rule says that if your number of pi electrons is equal to 4n plus 2, then you're going to be aromatic. If the first three criteria are true. If you only have 4n pi electrons, you're going to be anti-aromatic. Okay, and in both of these, keep in mind that n is an integer. Which is going to be 0, 1, 2, 3, so on. I go dot, dot, dot. So it has to be a whole number or 0. So that's kind of what we're looking at in terms of n. So if we take a look at some of our examples here, we look at benzene, we would count the pi electrons as whatever electrons are in the pi bonds. So we've got 2, 4, 6. So we've got 6 pi electrons. That's going to fall into that 4n plus 2 category when n equals, 1, right? So if n is 1, 4 times 1 plus 2 is 6. So that is why benzene falls into this aromatic position, because 1, it's obviously cyclic. 2, we know that benzene is flat. 3, we do have a p orbital on every single atom because we've got a pi bond on every single atom. And then we check off this correct number of electrons in that box, okay? So if we look at cyclobutadiene on the other hand, so I've got 2 pi bonds, so that's a total of 4 pi electrons. That's definitely going to fall into the 4n, where n equals 1. Okay, so it is cyclic, it is planar, it's got a p orbital on every atom, right? 1, 2, 3, 4, and it falls into that anti-aromatic number of electrons for Huckel's rule. So this guy is anti-aromatic, okay? If we look at the last one, the cyclooctatetraene, let me try that again. Honestly, the 8-membered rings are the hardest for me to draw. I can draw 7s just fine. Okay, so this is an instance where if we count up how many electrons we have 8. Okay, so if we just immediately looked at this and said, okay, 2, 4, 6, 8 electrons, that's going to fall into the 4n. So shouldn't this be anti-aromatic? But to avoid being anti-aromatic, because this actually has a little bit more wiggle room because it's a bigger size ring, it is actually not planar, okay? So to avoid all of that situation, it essentially separates out its pi bonds so that they aren't really very well conjugated with each other. And because they aren't very well conjugated with each other, now it is avoiding anti-aromaticity and becoming a non-aromatic molecule. So the way that this actually looks, I'm going to try my best to draw this out. Okay, it actually adopts more of a boat type shape. So when you build a molecule of this, actually, I'm going to pause this real quick and build a model real quick. Okay, got my model. So when you build a model of it, you see it's actually more of a boat shape than anything. And it's very, very, like, I can't actually bend it to be flat, right? So this is definitely not planar. If we think about where our p orbitals are, we essentially have p orbitals here and then p orbitals there. So they're about perpendicular to each other. So we don't even really have resonance transferring between them. So it avoids all of that conjugation and the whole horrible bits about anti-aromaticity by adopting this type of conformation where it's more of a boat. Okay, so that is helping us to avoid that anti-aromatic business. Screen share back up. So this is not planar and it is non-aromatic. Okay. So after talking about that last example, one of the really key points that we want to think about when we're thinking about aromaticity is we really want to keep in mind that molecules are going to adopt the lowest energy form. Okay, so we need to always have that in mind as we're trying to assign whether something is aromatic or anti-aromatic or non-aromatic. Because if a molecule can be aromatic, it will be. Okay, so if it has the ability to become aromatic, it's going to adopt whatever conformation it needs to be to stay that way. Okay, if a molecule can avoid being anti-aromatic, it will also do that. Okay, so just like we saw with the cyclooctatetraene, it's much, much better to adopt a non-planar, non-aromatic conformation than an anti-aromatic one. So it's definitely going to just sit in the nice, happy, non-aromatic zone and not be anti-aromatic if it can avoid it at all costs. So always keep in mind that non-aromatic is better than being anti-aromatic. Okay, we want to always keep that in our minds. Okay, so let's talk about a couple of examples of in terms of how you're going to see this stuff. Because we're pretty much going to be looking at a bunch of molecules and you'll have some practice doing this and asking yourselves, is this aromatic, non-aromatic, or anti-aromatic? And we want to be able to answer that confidently because that really dictates what type of chemistry something can do. So we want to make sure that we're good at that. So let's take a look at a couple of examples here. Okay, so we're going to look at this one. Going to be a series of 5-membered rings and then one odd man out, just because I want to show you guys this example. Okay, so we're going to look at these 4. And we're going to determine whether they are aromatic, anti-aromatic, or non-aromatic. Okay. All right, so let's look at the one on the left first. So if we are trying to go through this, we can say, is it cyclic? Yes. Is it planar? Probably. I would say for the planar, if it's a small ring, like, less than 7 carbons or 7 atoms, and it's fully conjugated, it's probably going to be planar. You can always build a model if you're not sure. I generally will not be trying to expect you to know what's going to be planar and what's not. It's going to be obvious in other ways. So planar, we'll say probably. Do I have a p orbital on every atom? In this case, I absolutely do not, right? I have up here an sp3 carbon. So I don't have a p orbital on that carbon. So therefore I have a break in the chain essentially of p orbital, p orbital, p orbital, p orbital, and then no p orbital on my 5th carbon. So I don't. So as soon as one of those things fails, I'm automatically going to non-aromatic. Okay, let's look at the next one. So we'll do the same thing again. So cyclic, yes, definitely. That's the easiest one to answer. Planar, again, probably. We've got a situation where it is a pretty small ring, so it's less than 6. It's most likely going to be planar. So I'm going to give it a check mark here. Does it have a p orbital on every atom? Let's check. So I've got p, 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 right, from all those pi bonds. I've got a carbocation. We know that carbocations have an empty p orbital. So yes, I do have a p orbital on every atom. So do I have, how many electrons do I have? I've got pi electrons in my 2 pi bonds. So I've got 4 total. That's going to fall into my 4n, where n equals 1. So that one is going to be anti-aromatic, and there's not a whole lot that I can do about it. Okay, and if you go into kind of more advanced levels of chemistry, you'll see that even anti-aromatic molecules really can find ways away from anti-aromaticity. So generally what something like this would do is that carbon would get yanked way up out of the ring, so it would actually stop being planar. You'll see a lot of kind of distortion of the actual structure in those anti-aromatic compounds. So there's a ton of distortion that happens to these guys. We won't go much into that. We're just going to leave it at like anti-aromatic for here. All right, let's go on to the next one. Okay, so if we've got another 5-membered ring, we're going to say that we are cyclic, we are planar. So for p orbital, that's an interesting question. So we're going to give those 2 check marks. So for p orbital, we have to decide, is the lone pair in a p orbital? Okay, because we've seen that lone pairs can be in p orbitals or they can be in hybridized orbitals, depending on the situation. So this is absolutely one of those times where we again have to think about, where are my lone pairs actually sitting? Okay, so this lone pair, we need to think about where it wants to be. So this is back to these questions. If it can be aromatic, it's going to be. If it can avoid being anti-aromatic, it's going to be. So really, we need to think about where is the most beneficial place for this lone pair to be. So if I put it in So let's put it in the p orbital for now, and then we're going to count it as part of our pi electrons. So that's assuming I can do resonance with that lone pair, go into my pi system with it, and it is part of that conjugation system. Okay, so if I do that, then I've got 2, 4, 6 electrons. I've got 6 pi electrons. That's going to fall into 4n plus 2, where n equals 1. So that falls into my aromatic number. Okay. If I said the lone pair in an sp3 orbital, because that's pretty much my option. I'm either sp2 on that carbon, it's in a p orbital, or it is sp3 and not delocalized at all. So with my lone pair in an sp3, I would have 4 pi electrons. Actually, it wouldn't even matter. If I had it in an sp3, I don't have the p orbital on every atom, so it would be non-aromatic. And the number of electrons doesn't even matter. Okay, so out of the two options here, we're going to pick the lowest energy. So we're going to pick that guy, and this doesn't happen. So the lone pair is in an, is in a p orbital, and the carbon is sp2. Okay, so that we've got p orbital in every atom, we've got 6 pi electrons, and that's all making it so that that whole thing can be aromatic. So let's look at the next example, and we'll be able to put this to practice again. So cyclic, yes. Planar. Again, this is one of those times where it's a little bit hard to tell. We could build a model, but we'll probably also answer the question along the way if we can. So sometimes it's okay to skip the planar one and go to the p orbital and the electron count. Okay, so p orbital, I again have a situation where I've got lone pairs that can be part of that pi system, or maybe could not be part of that pi system, depending on what is going to serve that molecule the best. Okay, so if we consider the lone pair, or one of the lone pairs, so in a p orbital, I would have 2, 4, 6, 8 electrons if it's in a p, but that goes into my 4n category where n equals 2. Okay, so that puts me in anti-aromatic territory. Okay, so we do not want to be anti-aromatic. So let's see what happens if we put the lone pairs in sp3. Okay, so what happens if that oxygen isn't hybridized at all? It's just sp3, or isn't conjugated at all. It's just in an sp3. Everything is sp3 orbitals. So if I do that, then I could be non-aromatic. Okay, so that's the one that I'm going to pick. Again, it is lowest in energy. That's where we're going to sit. It's much happier for that oxygen to just be sp3 hybridized, so it doesn't have conjugation, doesn't have resonance. So let's just write that down. There we go. So no resonance here. That way we make sure that we have not anti-aromatic and we just have the non-aromatic. So that's going to be sp3. We're going to avoid the anti-aromaticity by doing that and be a much lower energy structure overall. So we are not going to do this, and we cannot draw resonance without oxygen. So that is something we need to keep in mind for future reactivity, where something like this, we would just be able to do alkene reactions on it rather than the aromatic reactions that we're going to learn. Okay, so we will be doing more practice on this in class and on your daily problem set, obviously. So we will keep talking about it and bring any questions that you have. And have a good one. I'll see you later.